Buenas tardes y bienvenidos a otro martes de coloquio. Bienvenidos a la comunidad del ICAT. Estamos transmitiendo a través de Zoom y también a través del canal de YouTube oficial del ICAT. En este martes de coloquio tenemos la participación de la doctora Elodie Strupiechonski del Instituto Politécnico Campus Querétaro. La doctora nos va a hacer una presentación en inglés, titulada Toward a Terahertz Microfluidic Platform. Entonces comenzamos leyendo la semblanza de la doctora Strupiechonski. She received a Ph.D. in physics from the Université Paris in France in 2013. She was a postdoctoral fellow at Harvard University until 2016, when she became the head of the laboratory for Terahertz Optoelectronics at the Center for Research and Advanced Studies for the National Polytechnic Institute of Mexico in Querétaro, Cinvestav. Her lab integrated with the National Laboratory for Terahertz Science and Technology in 2018.
Hola, no has entrado al...
She's currently a CONACyT research como investigadora por México at Cinvestav Querétaro and holds a National Researchers System of Mexico Accreditation SNI Level 1. Her research focuses on developing novel devices and innovative techniques involving terahertz radiation, and she is particularly enjoying solving transdisciplinary problems. She is especially in near to far infrared spectroscopy and imaging and investigates light to matter interactions in a wide range of natural and artificial materials such as metamaterials, structure, polymers, semiconductors, 2D materials, and chemical and biological samples. So, Dr. Strupiechonski, we are ready to hear your talk.
Thank you so much, Carlos, for the presentation. Thank you for the invitation. It's really nice for me to have this opportunity to share a little bit of our activities in our laboratory for Terahertz Optoelectronics here in Cinvestav, Querétaro. We are not too far away from you. And so one of the objectives of this talk is to hopefully generate more collaborations with you. And so thank you so much for the introduction. Let me share my talk. It should be now in full screen.
Yep.
Okay, great. So I'm going to stop the video just to ensure good quality of the sound and the slides. And I'm going to start. Okay, so as Carlos said, so today I'm going to present one of our ongoing projects, which is to build a platform for terahertz microfluidics. So it is very, let's say, challenging to do so. And I'm going to hopefully explain why is it challenging, but more importantly, why is it necessary? Why is it interesting to do it? And how we propose to achieve this. It is not changing slide. Okay, so I'm gonna do it like that. Maybe I can have also a, I'm looking for the laser pointer. Sorry about that.
It's below at right. Like a mark.
The pointer options. Okay, do you see it?
Yeah.
Great, thank you for your patience. So this is the content of this presentation. I will give you an introduction to our laboratory, our lab members, and our activities. And then I'm gonna give you a little bit of an introduction about what we call the terahertz gap, and what are the solutions that we in the terahertz community are developing. And at ICAT, you have one of the few groups. We have very few groups in Mexico. This group is led by Nasser. You probably all know him. And then I'm gonna shift the focus towards biochemistry, applications in biochemistry, and how terahertz technologies are relevant in this area. And I'm gonna present our preliminary results and some perspectives of this work. So we are in the laboratory for Terahertz Optoelectronics. We are in Cinvestav, Queretaro. We are one of the three laboratories that form the LANCYTT, Laboratorio Nacional de Ciencia y Tecnología de Terahertz. And here you can find some details if you want to look at our website, and if you want to contact me. We are funded obviously by CONACyT. This is a very important source of fundings for us. So I thought I'd mention it right from the beginning. And okay, so we are specialists of terahertz radiation. And basically, this is a new field of research where we can do imaging and spectroscopy. Okay, and I'm going to tell you a little bit more about it, but basically this is the region of interest between 100 gigahertz and 10 terahertz, more or less. We can extend beyond that. Around 10 terahertz, it's what people start calling long wave infrared devices or technologies, and below 100 gigahertz, we're entering the millimeter wave region. But all of this range, basically, we are dealing with electromagnetic radiation. So there is no reason why, I mean, there is nothing special about these waves, except that it's really hard to produce and detect them, and that the material properties are completely different from what people are used to find in the visible range or in the low frequency range. And so we have activities where we develop applications of these technologies towards imaging and spectroscopy. And in particular, we like to think of these techniques as non-destructive and non-ionizing, which is one of the major advantages of these technologies. And on the other hand, we also develop projects where we propose new emitters and new receivers for terahertz radiation. Okay, and so here you see some examples that it is not included in the scope of this talk in particular, but I'm happy to develop this in another occasion, where you can have sources that are lasers. And this is an example of a solid state, really small terahertz laser that is based on quantum cascade laser technology. Then you can have other type of photoconductive antennas for receivers, and FET, field effect transistor, high electromobility transistor based kind of technology, where we couple all these nice devices with antennas or metasurfaces to engineer the beam output. So these are the main collaborations for today's talk, and we have two probably on the way. One with someone in Inaue, Dr. Carlos Treviño, and hopefully with Professor Nasser here in ICAT. But for now, one of our main collaborators currently in France is Jean-Paul Guillet. He's a specialist in the integration of Terahertz technologies for imaging, sensing, and spectroscopy applications. So with him, we have a lot of internships that are being programmed and a lot of technology transfer from their labs to ours. We have a very recent but very productive already collaboration with Dr. Mario Alan Quiros Suarez from CEFATA-UNAM here in Queretaro. He is a specialist in artificial intelligence, and we are going to apply his knowledge for image interpretation when we generate images in the terahertz range. And from the same institute, we have an important collaboration with Luz Maria Lopez Marin. She is helping us with all the materials that are related with biomolecules or interactions between proteins, etc., which is very important for this particular presentation today. Here are the students involved in this project. Currently, we have maybe one or two that are incoming that are not appearing here. Probably the next time I get an opportunity to present these activities, they will be on this slide. We have Manuel Alejandro Justo Guerrero. He is a PhD student about to graduate, so he probably will graduate in January next year. He will be looking for a postdoc position. He is behind most of the work that has been happening in our labs for the last, let's say, 5 or 6 years, because he started as a master's student. I can highly recommend him. If you have an idea, an opportunity for him, then send me a quick email and I will be very happy to relay that to him. Pedro Angel Cristian Silva will be working mainly on terahertz imaging system. Humberto Vasquez Sanchez, he is a student in co-direction at UNAM FATA. He will be the one making the junction between terahertz data and artificial intelligence. Armando Becerra Hernandez, he's a PhD student in FATA as well, working with Dr. Luz Maria. He's involved in everything that deals with biomimetic nanostructures, proteins, etc. So let's introduce you to Terahertz technologies and what we mean by that, what are their applications. So here is the slide that I like to put there because, especially for students, I like to debunk a little bit what we call T waves, terahertz radiation, terahertz frequencies, etc. We are talking about an electromagnetic radiation wave. It's the same as what people use in Maxwell's equations. It completely obeys the 4 Maxwell equations, which are summarized here in the differential form. It is an oscillating electric field coupled with a magnetic field that can be propagating or can be in resonance in a device. There is nothing special about it except for its frequency. Okay, so the wavelength associated with 3 terahertz, for example, is about 100 micrometer. So it's extremely large compared to the wavelength in the visible, which are hundreds of nanometers. But it's kind of small if you compare that to radio waves, which can be a centimeter long or meter long electromagnetic waves. I like this slide because this is something that everybody can do to have an idea of their community, what is emerging, what is already mature, and what are the keywords associated with it. It can, if you are a student, it can tell you how young your field is. It can tell you about what are probably the main domains where you will find applications, etc. So here, from this set of words, what we do is called cloud words. We give them a higher font for the number of times these keywords are associated with publications dealing with terahertz in general, terahertz applications, terahertz fundamental science, etc. So what you can see from these keywords is that, first of all, it is still in the lab. You can see these very fundamental fields associated with this technology, which means that it's not really mature. When it will be mature, you will have more larger fonts for engineering type of applications. But what is really interesting to me, and is very important in particular for this talk, is that it's multidisciplinary. All the keywords associated with this field are highly diverse. You can see emerging computer science, which in this particular talk I refer to with the keyword of artificial intelligence. Okay, but basically, yeah, this is a trend that is clearly emerging here. Here are the kind of most frequent terms that you can find now within the core of the scientific papers that are being published. And again, the size font will tell you how often you can find these terms. Okay, so you can see that, for example, I was mentioning quantum cascade lasers. They are probably one of the main source of continuous wave, sorry, in the terahertz range, continuous wave emitters. You can see that spectroscopy, of course, is important. You can see the type of simulation that we like to use, finite difference time domain method, things like that are very important for us to sort of direct our research, etc. So here in this slide, again, all this data comes from Scopus. You can generate these for your own field. It's all available freely, openly on the internet. So here, what I was interested in looking at is where is my community? Okay, so Scopus can tell you the number of publications that contain terahertz in the title, and the countries of the authors, of origin of these, or let's say of the affiliations of these authors. And so what you see here is that in Europe and in Asia, our community is really well represented. And then in North America, where of course I included Mexico, okay, is also really well represented. Now, if you zoom in, and if I was to show you how many groups are producing scientific papers related to terahertz in Mexico, we will be maybe 5 or 6. So there is a lot of room in Mexico to develop terahertz science in general. Now, if you want to know how mature and how important is your field of research, you can do something like that. So here, for example, I represented something that I know really well, is technologies that are in the mid-infrared range. Why? Because we all now know that in our cell phones, we have mid-infrared cameras. You are all aware of the thermal cameras that the military uses. sort of make an image in false colors based on the temperature of the objects surrounding us. So this is very important for night vision, for example. So we all know that all these technologies, they started to become available to the large public in between the year 2000 2010. Okay, so here you see the number of publications per year that you need to reach in your field so that your technology can become available in commercially. Okay, and now I'm going to superimpose the same data, but now exchanging the term mid-infrared with the term terahertz in the title. Okay, so we started later, and then by 2020, we were already reaching the rate of production of scientific paper than the mid-infrared community was doing. Okay, and look at what happens next. We are booming. So that's why I like to call that the terahertz revolution. If you are a student and you have the choice between developing a project in the mid-infrared range or in the terahertz range, I highly suggest you go for the second one, because this is also highly correlated with the amount of funding that is available for that particular domain. Okay, so here I wanted to show you why there is what we call a gap in the terahertz frequency range. So here you can see the frequencies that are from small to large, and the corresponding values of wavelength from small to large in that direction. Okay, so you can find the visible range here is really small. Okay, this is what people are most used to think of when they think of electromagnetic radiation. They think of what their own detectors can detect, and we're talking about our eyes, right? And so we're talking about hundreds of nanometers in wavelength and thousands of terahertz in frequency. So if you work in this area, you're probably calling your technology photonics. Now, if you move toward the other side of this range, you will find your microwaves, millimeter waves, and radio waves. And if you work in this area, you probably call your technology electronics. Okay, and if you are interested, for example, from the community of electronics to push your frequency of operation towards larger frequencies, you will find that your output power is going to decrease drastically. And there is a lack of sources and detectors above hundreds of gigahertz that are as efficient as in the radio waves. It's really hard to find. Okay, now if you work in photonics and you're trying now to increase your wavelength of operation, you will find the same trend, that your output efficiency is decreasing as you move across that trend. And this is problematic, and this is why we call that the terahertz gap. So in this range of frequencies from roughly 0.3 to 30 terahertz, okay, there are as many applications as you can find in the rest of the frequency range. Okay, it's just that we were not able to explore them for a long time, but now we can. Now we have technologies that is being developed that allow us to reach this range. Okay, so here is are examples of all the technologies that we all know that are ordered on the frequency range here from small to high frequencies. And you can recognize that, for example, for telecommunication, it's really interesting that you have like 3G, probably 4G here, 5G is already in the terahertz range. So 6G is gonna definitely, I mean, they will need us. And in the visible range, then you have extremely ionizing high energy radiation being used to generate images, for example, of bones through tissues. And what we're discovering with terahertz waves is that you can find complementary imaging, but now you're using radiation with an associated energy that is in the range of milli-electron volts. So it's challenging to work there, but it will provide complementary solutions in the case where ionizing or destructive techniques are not really desired. Here is a zoom in on that frequency range, and this is what I like to call the 1 terahertz limit here. And it's very interesting. And here I'm focusing on the properties of the materials. If you go above 1 terahertz, you're really complementary with mid-infrared spectroscopy, where your molecules continue to have a fingerprint. So you will have really, on that range, you will have really molecular fingerprints that will allow you to identify molecules. Okay, this is what we call the resonance area. And if you go below 1 terahertz, you enter what we call the transparency area, where you can do really nice imaging applications. Okay, and we call that the transparency area because most of the dielectrics are transparent. So you can really do non-destructive imaging for applications in industry or in security. I'm gonna be really quick on that slide. This is where we can compare the efficiency of our detectors and our sources, and you can see that it's really decreasing around 1 terahertz for the sources, and for the detectors, you want to minimize this key parameter, which is noise equivalent power. You want this as small as possible, and you can see that there is a lot of work to do to reach what we can reach with cryogenic detector, right? Okay, so here is a summary of the applications that are starting to emerge now in the medical field with the group of Enrique Castro-Camus, for example. When he was at CEO, there was a very nice application for imaging of diabetes feet from patients suffering from diabetes. Is very important to be able to detect in an early fashion the formation of a wound, which can be completely not detected by the patient itself until it becomes really, harmful, and amputation can follow. So for these kind of applications, here is an example of imaging of a cavity in tooth. So this normally you would do with X-ray imaging, and X-ray, you know, is ionizing. So you want to minimize your exposition to X-rays, whereas here with terahertz frequencies, really the energy associated with each photon is really small. In astronomy, so this is really what, for example, you will find in Inaue, Puebla, in the group of Dr. Carlos Trevino. You can look at the sky and you can have information about early times after the Big Bang, if you are interested in this kind of studies. 1 terahertz corresponds to picoseconds kind of times. You can monitor the atmosphere. For example, currently it's mainly done in the infrared range, in the mid-infrared range, but there is a lot of work being developed now with terahertz waves as well. And in biotechnology, so this is probably where I would locate the work I'm presenting today. And this is because, you know, proteins have dynamics that are intermolecular, that are predicted to happen at very small energies that correspond to terahertz frequencies. In security, so this is really one of our emerging applications in the lab. This is towards imaging. Here is a very well-known paper. It's been, I think, out there 15 years ago. They published that, where they demonstrated that not only they can image an hidden powder sample inside an envelope without opening it, but they can at the same time identify it because they have access to the spectral footprint of that particular powder. And so here they are identifying with false color. Yellow is attributed to, I think if I remember correctly, methamphetamine, and then blue was for another illicit drug, and red was for another illicit drug or an explosive. And so in the industry now, there is a lot of interest because you can do imaging like that. And so you can have a real-time detection of defects on the production line instead of producing an entire lot and then picking just one product, completely destroying it. And if you find a defect, then the entire lot goes to the trash can. Well, in principle, with the aid of artificial intelligence, you should be able to develop a system where a human intervention is not necessary anymore. It's completely non-destructive, and it will be real-time decision-making that will save you a lot of money if this is your company. Okay, so we're going to focus on biochemistry now. Just looking at the time, yeah. Okay, so this is really the motivation here. If you read this paper, what is really nicely explained here is that in the infrared range, you can have access to quaternary structures phenomena, interaction between light and functional groups, vibrational modes between two atoms in a large molecule. And it's very important to determine the structure, the atomic structure of a molecule, for example. And if you go towards smaller frequencies, then as you go in these directions, you're probing longer range interactions. So you're probing now conformation modes of the proteins, folding and folding, interaction between proteins, etc. And then as you go below 1 terahertz, then you can access information about the secondary structure and then the primary structure. Okay, so this is really important. It's highly desirable that you can do that. One of the problems, though, is that most of the molecules of interest are going to be in solution. Okay, we are talking about applications in chemistry and in biology, and if you want to be able to study the interaction between molecules, you want them in their preferred medium because then they can really be fully functional. People normally, what will they do? They will dry their sample and they will make their analysis on a dry sample. And they're finding that, well, they're destroying the functionality of the molecules they're trying to study. Okay, so these preliminary results, they are really from a physics point of view, is really a technological kind of a conceptual kind of study that was presented in that conference. And also we have a manuscript being revised in IEEE transactions on Terahertz Science and Technology. it's very important, though, to focus on these details so that you can overcome these problems. So this is the presentation of our setup. We are using an FTIR. So FTIR is a Fourier transform infrared spectrometer with a Michelson interferometer. We're using a broadband source, which is a mercury lamp. And this is the sample compartment, so you can follow the beam path that can interact with an accessory and a sample, or just a sample in transmission. And then our detector is also specific to terahertz. So we are emitting here black body radiation that is peaked in the UV, but we are working in the tail of that emission range. Okay, and our detector is a DT, LA, GS kind of detector. Everything is at room temperature, and we are working under vacuum, which is really nice because, as I said, all the molecules that are in air, CO2, water, everything that is in your atmosphere is going to be leaving a very strong fingerprint in the terahertz range. So here we're working in vacuum, which was one of the challenges that we had to overcome when you want to work with liquid samples or biological samples and you don't want them to evaporate in your vacuum atmosphere. And this is the accessory that we're using. It's called an ATR. ATR stands for attenuated total reflection. And it has a crystal here. It's a diamond prism. It's really small. It's 2 millimeters by 2 millimeters, the top square area where we are depositing the sample. And the beam enters from the right here. There is a set of mirrors that are deflecting the beam towards the prism as well as focusing it. And then it's going to be redirected towards the detector on that side. And we are going to focus on the physics really happening here and why it is important to understand that. So here we present what you will get with this accessory if you deposit a droplet of water on it. Okay, you find that in the mid-infrared, you have the very well-known absorption peaks that correspond to some stretched and bended modes of the water molecule. And then when you enter into the terahertz frequency range, suddenly you have a drop, dramatic drop of these intensities. And this is really not desirable, because if you are interested in adding some analytes in this water droplet, your intensity levels now are close to your noise levels, and it's going to be really hard to detect small amounts of analytes. So this is typical of what people will see, and they will just say there is a lot of absorption from water here. What we demonstrate is it's not only absorption, we are losing a lot of light that is refracted. Okay, and so basically, if we can understand this well enough, maybe we can increase this curve. We can really, excuse me, you can really improve the signal that you collect in your sample. And this is important because, as I said, here you have the collective modes. You will have information about protein-protein interaction, protein-water interaction, etc. And so this is normally what you would find. This is our prism, diamond prism. This is the incident beam at an angle of incident θ1, which is in our case 45 degrees. We cannot change it. And you would have a reflected beam. Normally what people are trying to satisfy is the condition for total internal reflection. In that case, you don't have a transmitted beam, but you're working with an evanescent beam that is going to be interacting with your sample. And there is a lot of work being done with the Beer-Lambert law and the Snell's law to understand and interpret the data that you will get from such an accessory and an experiment. So what we are arguing here and we're demonstrating, and it's really interesting, it's very important, is that in the case of water and in the case of any lossy sample in general, and it's not only in the terahertz range, it can be in any range of interest. If you have a lossy material here at this interface, you will have a transmitted beam, and there's nothing you can do about it. And it's not the decrease that you're gonna read in your data does not come from attenuation in the evanescent field. There is no longer an evanescent field. And so what we did is that, okay, we took from the literature the optical values of these parameters for water N and K. And you can see, in fact, yes, it is true. The K value is increasing dramatically, but for frequencies below 1.5 terahertz. Above it, it's fairly stable, I would say. And in the meantime, the real part of the refractive index is also changing a lot, and it's approaching the one of the diamond. So we can do simulations. We have an analytical model for that. These are CONACyT simulations where you can extract the pointing vector. And the pointing vector is only here if you have a transmission. So you can understand all that. Another feature you can extract is the penetration depth of your field in your sample, and this is also an information that spectroscopists need to know in order to correct their data. If your penetration depth increases across your frequency range, you need to take that into account, because you will have the impression that your absorption increased when in fact it's the volume of the sample that is being tested that is increasing. So in red, this is what people think. This is how they can calculate the penetration depth if they are using the Beer-Lambert law and the Snell's law, but this is only valid for low lossy samples. Now, this is what our analytical model predicts, and in green. So you can see that we can calculate this value, evaluate this value across the entire frequency range. This is what our CONACyT simulations tell us. So there is an excellent agreement between the analytical model and what you can get from finite element method simulations. And so if you compare now these capacities to the experimental data, this is what the analytical model predicts, is in a good agreement with what we can measure, and this is what comes from the CONACyT simulations. Okay, so now we understand the behavior of water and we can reproduce it, but how can we improve it? So our trick was to use a mirror on top of the water, and we created thin films of water, and really the idea was to retrieve the refracted beam and send it back towards the detector. So it's no longer an ATR experiment now, it's a sort of a double transmission through the water film type of experiment. Okay, and what you can see here from the pattern that you see there is that at the beginning for large thicknesses, you don't have a really nice pattern where you have superposition of two beams that would be equal intensity. You actually see the pattern of a propagating wave in that direction, and then we correct it slowly. And this is what we promised. So this is what we get. This is the bulk water. You would be in the range of 30% in your reflectance, and then rapidly going down for frequencies below 8 terahertz. And then as you decrease the thickness of that film, you retrieve a lot of signal. And this is understood with our analytical model, and the results from CONACyT simulation also are in really good agreement with this model. So this is a summary of that work. Traditional model for ATR spectra interpretation does not apply anymore. There is no longer an evanescent field. Transmission contributes to the loss that is perceived in the data. penetration depth spans tens of microns, which is very important to be able to calculate. Now we can calculate it, and the signal can be retrieved using a mirror to improve sensitivity. So now that we have a better sensitivity, we can detect small quantities of analytes. And this is the project that we are trying to develop now, is to add an accessory to the accessory, where we can have a mirror at a fixed distance from the prism and really retrieve really nice intensities of signals, and then maybe functionalize it, and then maybe use resonators and observe the shift in frequency when they interact with some proteins or some analytes. One of the ongoing projects in the lab that is connected to that work is the detection of glyphosate and other harmful pesticides, where you can see here that in the mid-infrared range, we can detect the presence of glyphosate in solution. But if you remember, in the terahertz range, really the small intensity they do not allow to really perform any good quality studies. So hopefully with this now development, we will be able to do that. And this is another ongoing project in the lab, and I want to mention it because I would like to invite Professor Nasser to join us on that project. This is about terahertz imaging. This is the kind of signals that we can retrieve. This was the source is a startup company called LANCYTT, where they are proposing a system to do this kind of imaging. In the pharmacy industries, is highly desirable to be able to, for example, know if the instructions are present in the packaging without opening it, but they cannot use X-ray radiation. X-ray radiation will interact with the molecules, the active molecules, and potentially modify them. So they are looking for an alternative, and terahertz frequencies could be a good alternative. And so, of course, now the way you're going to interpret that signal currently is really limited, and I think we can extract a lot more information using artificial intelligence kind of tools. With you, I thank you very much for your interest and your patience with me, and I will leave the floor to Carlos for the question.
Thank you so much. Sorry, a second, because we have some. Okay. Thank you so much for your nice presentation and very interesting presentation. Now, the floor is open for questions and comments from the public. You can make your questions either in Spanish or English.
Sí, les hice la presentación en inglés, pero podemos hablar en español.
Claro. Verena.
Thank you very much, Elodie, for your presentation. I think it's very interesting, especially the imaging applications with terahertz. I am wondering about dimensional uncertainty induced when monitoring with terahertz objects, like you mentioned lastly the chemicals on the I guess it's a type of terahertz microscope, or I'm not sure. If I would like to measure dimensions, how good can the information be, maybe compared to infrared images?
If you are interested in resolution in imaging, for example, if that was your question, right? Yeah, yeah. So you're limited by the wavelength. Okay, so we are using larger wavelength than in the mid-infrared, so we will have a smaller efficiency in the resolution. So for example, in the mid-infrared, if you're using 1 micrometer wavelength, this will be your resolution, more or less, maybe half of that. In the terahertz range, this value reaches hundreds of micrometers. So this will be your resolution, 100 micrometer.
Okay, and at what distance would it be recommended to monitor the object?
So it's a non-contact kind of imaging. The distance is really depends on the depth of field that you're trying to reach. So we are using similar technology for our lenses. I mean, the concept is the same as the lenses in the visible range, where if your focal length is really long, you know, and so you're very far away from your sample, you're going to have a large depth of field, and but you might lose a little bit in contrast. And then if you approach your system, you change your focal length, and you get really, really close. Now you're really precise in your depth of field, and you get a little bit of contrast, but then, yeah, you lose depth of field. So it's a compromise, and you decide it by when you design your focal system between the sample and the imaging system.
Okay, if the part of interest is rotating, would this be a limitation for the method? I'm thinking about tomography applications.
For tomography applications, for imaging, right? In tomography applications, basically what we are doing now for tomography takes some time of integration if you want to have a good signal over noise ratio. So ideally your sample will not move for a few minutes. I don't know if that answers your question. I'm trying to change slide, but for some reason it does not let me change. Maybe if I stop share and then I share again. Maybe I can do the previous, yeah. Okay, so for this kind of applications, Verena, is that what you're interested in?
Yes.
Okay, so this, for example, this is a technology that's developed by LANCYTT, and what we want to do actually, so this technology emerged from Jean-Paul Guillet's group in EMS in France. And there is a version of that we want to do that would be completely open source. And we're using in that case what is called a frequency modulated continuous wave radar. Okay, and so this frequency range is in the order of hundreds of gigahertz, which is sub-terahertz. Okay, so this is the kind of signal that is generated at this point here. Yeah, and to generate this image, you can see the size of it. It's 11 centimeter wide and 8 centimeter high. And in depth, we are able to get information again in the range of centimeters here. And the resolution is probably 100 micrometer or 2. Okay, I think. Yeah, or maybe close to below 1 millimeter. So this is what you can get for now, and you can sort of recognize this pattern that comes from the fact that the sheets of the material are not completely flat, etc. You can also see in one of these images that is not shown here, if a peel is missing, for example. So this is the kind of signal that you get, an amplitude as a function of depth position. And this is how it looks like. So this is right now interpreted in false color for each pixel. So this is for one particular pixel. And the signal is sort of extended in the Z direction. So this is kind of information, this kind of images that currently are commercially available. So hopefully in the lab, you can do a little bit better than that. You can change the frequency of operation. And this is the kind of things that we are interested in my lab.
Thank you very much. Very interesting.
Thank you.
Thank you so much, Verena. We have another question from Mayo Villagrán. He's asking, how many terahertz sources you have and in what range are they tunable?
Okay, we have a broadband source, as I said, which is a mercury lamp. It is not known for being a terahertz source, but look, this is the frequency range that we can achieve in our setup currently with the FTIR spectrometer. So it's in wave numbers. Spectroscopists, we like to look at this data in wave numbers, but for example, here we are at 1 terahertz. Here, this is 3 terahertz, and somewhere here are going to be 10 terahertz, and then we enter the mid-infrared, and then we can also access the near-infrared. Okay, so this is one source, and it's really broadband. It's actually a set of 2 sources that we can change the configuration. This is for the spectrometer. For external sources, we currently have a quantum cascade laser that is emitting around 3 terahertz. It's a frequency, a difference frequency generation kind of quantum cascade laser. We received it from a collaboration with the group of Misha Belkin, who was then in UT at Austin. It was in a project that was funded by a fund called CONTEX. It's CONACyT with the Texas universities. And the idea was to build a compact imaging system at the time. That was very challenging, a very short-term kind of project. But yeah, we have this QCL. It is not what I would call a tunable source, though. But it's emitting in the mid-infrared at 2 colors that we are mixing to generate the terahertz frequency. You can tune it basically with the temperature, because it's a solid state system. You know, the refractive index of the dielectrics are going to slightly change depending on the temperature. And if your refractive index changes, then the properties of the cavity are going to change. And so the emission, the output wavelength is going to be slightly tuned because of that. So I would say the tuning that we can get is probably around 10% around the frequency of emission. But also, so compared to let's say a more traditional laser situation where your atoms are the ones emitting, the width of emission also is not as fine, is a little bit, the full width of maximum is probably also 10% around the frequency, the central frequency of emission. So this is another source that we currently have. We will, in the coming month, we will have a frequency modulated continuous wave radar source and detector. So this is with collaboration with Jean-Paul Guillet. Okay, and so what we are thinking for this source is probably going to operate around 180 gigahertz. And the width of frequencies, it will be probably from 150 to maybe 190 gigahertz. Okay, so but it's going to emit a frequency range. It's a ramp in frequency. Okay, so this is another source that is going to be available soon in the lab. And we are working with a potential collaboration with Nasser and Carlos Trevino, where we're thinking of titanium sapphire kind of continuous wave Terahertz emission. Okay, so in that case, it will be a little bit more broadband, and it would be a higher intensities. But this is really in the medium range for applications. So I don't. Have I answered your question?
Okay. Yeah. Perfect. We have another question from Dr. Nasser.
Hello, Elodie. Thank you for your talk.
Hola, Nasser. How are you?
Fine, thank you.
Thank you for the invitation.
Oh, you're welcome. Very nice talk.
Thank you.
Just curiosity, do you see any possibility of doing imaging with your FTIR system?
Oh yeah,
like
we did.
scanning a sample. Have you done that?
We did that. I'm not showing it. We did that. I was calling that hyperspectral imaging. Let me try to find it. Give me a minute. Do you want to include it? What we did was to hide a piece of PET from a transparent bottle, water bottle, and we hid it in polystyrene foam, white, completely opaque. And let me find it. And so we were able to retrieve the spectral information from each polymers, and then the convolution of the two spectra would tell us where they both are. And we would even be able to tell you what was the thickness of the PET film because of the interferences between the two interfaces, at the two interfaces. Give me a minute. It's really interesting that you're mentioning that. This was a very painful measurement, though, I have to tell you, because we were moving manually the sample, and every time you need to reach vacuum and integrate a number of scans. This will be.
What kind of resolutions did you get for that kind of measurement?
We didn't work on the beam spot size. And so we were getting maybe a 1 millimeter resolution. Depending on the frequency, we were doing that. Of course, over like between the range of 0.1 to 10 terahertz, or 15, I think even 20. Alors, maybe it's here. I can show you that page. Yeah. Okay, let me share again. Okay, so here you can recognize our setup, and it's not working. So this was done in the FTIR. Okay, and we placed a stage here. I will show you a photograph of that here, and we would do the raster scan manually with micro screws. And this is the idea, that you can image something that's hidden, and you can, for each pixel, actually, you're generating a cube of information. So you have a spectrum in each pixel. This is how we do it. We did it. So don't laugh, it's really artisanal right now. We have 2 micrometer screws here that are controlling the position of the sample. This is a diaphragm that we use to, in really a rough attempt of controlling the beam size. It was being focused by the parabolic mirrors that come with the FTIR. So really not focused. We could do better, definitely. And this is the sample. This is what we used as to do the demonstration of concept. This is the piece of PET from a bottle of, I think it was a water bottle. And we hid it inside, completely hidden. You see, we made an aperture here and we hid it inside the foam. And this was a spot size. I think we evaluated to be around 2 millimeters with in a different configuration where we had like openings in the mask. We were able to evaluate the spot size to be around 2 millimeters, roughly across the frequency range. And we took a few pixels. Yeah, and this is, for example, just from the interferogram. If you want, you can plot a black and white picture for each pixel, just looking at the maximum peak intensity from the interferogram. But then from the spectrum, you can recognize air from the foam from when there is superposition with the PET. So then you can attribute false colors to each pixel, and we decided to leave air white, to use blue for when you have the pure spectral feature of the foam, and red when you have a convolution of the two. And then we analyzed the spectra. It's not shown here, but you can take the spectrum from a pure PET measurement and the spectrum from a pure foam measurement, and mathematically calculate the convolution of the two. And this is really close to what you get in the red pixels. So we were very happy about that, but not very happy about the way we were measuring it. So it could be automatized for sure. We didn't do it yet.
Thank you. Very nice measurement.
Thank you.
Thank you, Nasser, for your question. Another question or comment here in Zoom or maybe YouTube? I have a question about the ongoing work you presented at the very end of your presentation.
Yeah.
You're planning to detect and quantify glyphosate that's my question, in solid samples or liquid samples. What are the plans?
So, yeah, it's excellent question. Thank you for asking that question. What we're doing is a very, very complete study. Here, for example, what you see here in blue, and I didn't take the time to detail it, but since you're asking, I'm happy to do so. We are taking a sample from a standard reference, which is, in this case, it was powder, pure glyphosate. I think it was guaranteed to be above 99.9% purity from Sigma Aldrich. And so this is the ATR spectral that we got in our setup from 20 to thousands of wave numbers. So it's really, you change the configuration of the setup and you can access the entire frequency range. Basically, it's really interesting. So you can see here that these peaks are characteristic of that particular molecule. It's well documented, etc. What we are adding here is this part of the spectrum that usually is reported with Raman spectroscopy. Okay, so this is really interesting to me because I'm trying to convince Raman specialists that we are complementary, because some, the most of their data they report is overlapping in range with ours, except that some of the transitions that they are probing are prohibited with Raman spectroscopy and are allowed in infrared spectroscopy, which is just, we are an extension of the infrared spectroscopy. So we have complementary data that is probably not being reported right now. So it's really interesting. I have a nice internal collaboration just about that, conceptually comparing the two the two techniques on some very well-known samples. But to answer your question, it's really hard to get glyphosate right now in Mexico. It's highly controlled. So our approach was that we had to be smart about it. I probably saw 50 milligrams of it within the last 2 years. 50 milligrams, that's all I had in my hands. It's really hard to get. So what we did is that we know that we can purchase it from the market. It's commercially available, except it's in either in solution, mixed with surfactants, mixed with molecules that will be used as stabilizers that are not, we don't know what they are really, okay? But basically this is what you will find in real life. So one of our goals is really to develop some spectroscopy techniques that could be taken outdoors and be able to determine quickly whether, for example, if you are producing apples and you want to demonstrate that your apples are glyphosate free, well, we should be able to tell you that, right? So that's one of the goals. So what we did was that we took that powder and we prepared a study as a function of concentration in water. So we used DI water and we were preparing concentrations of glyphosate. And you can see here we are not in the terahertz range, okay? And that's one of the problems that we had. But what we did is that we prepared ourselves to recognize the signature of glyphosate in the commercial solutions or commercial powders. So now we can continue with these really extensive kind of studies where you want to be able to monitor as a function of concentration or the kind of presentation that you will find might sometimes maybe in contamination in water, sometimes it can be recrystallization on at the surface of your product, etc. So we have basically standardized commercially available solutions and powder so that we don't need to use the standard anymore. And this is it's a lot of work that's being done in collaboration with UTC in Queretaro, with Dra Diana Alonso Segura. And we are, this is now you know the ambition of that project, and this was our way of avoiding probably shortage in our access to glyphosate.
Yeah, actually, it's pretty hard to get glyphosate. We in the Laboratory of Environmental Nanotechnology, we have glyphosate and also the main byproduct, the AMPA. Yeah. So if you want, we can provide you with some glyphosate.
Fantastic. Let's do it. Thank you. Okay.
Yeah, I can give you my email so we can share. And I'm asking for glyphosate because it's very challenging to detect glyphosate because it is a very small molecule with very low absorption in the UV visible spectrum. So it is quite difficult to detect and to quantify this molecule either by UV visible spectroscopy or by fluorescence spectroscopy, either by HPLC MSMS. So we have an HPLC MSMS mass spectroscopy device, and it's pretty difficult to detect glyphosate. So all the techniques that can facilitate the detection of this kind of compounds are very welcome. So
absolutely, yeah, we are not trying to say that this is the best way of detecting glyphosate, but definitely it's an alternative, and it will give us complementary information. And we are interested in maybe including you in the study, so that, for example, we've been asked, when I don't show it here, but in the spectral data from these commercial samples, there are some additional peaks, obviously, that come from all the additives that are present that we don't know what they are.
Yeah, additives and some stabilizers and some other compounds to reduce the lifetime of the main molecule in order to avoid this molecule to penetrate to groundwater. So
okay,
yeah,
so
let's
meet
there
afterwards and exchange ideas.
Yeah, of course.
Thank you for the proposition.
Excellent. So do we have any other question here? Maybe from Zoom or from YouTube? Okay, so that's it. So thank you so much, Dr. Strupiechonski. I hope I can pronounce
you did
correctly.
That very well. It's perfect.
So,
thank you.
Thank you so much to all the people were here in the seminar, and we will send you the certificate of participation in this colloquium. Muchas gracias. Muchas gracias a todos por acudir a este coloquio. Agradecemos también su participación con preguntas. Nasser, muchas gracias por facilitarnos la charla con la doctora. Y nos vemos el próximo martes en el siguiente coloquio. Que tengan un buen día. Hasta luego.
Hasta luego, gracias.
A todos.
Buen día.